Accurate flood detection using high-resolution synthetic aperture radar (SAR) imagery is a significant challenge due to the complex nature of SAR images, which can lead to overestimation of flood extent. Existing convolutional neural network (CNN)-based change detection methods have limited performance, as they fail to model long-range dependencies. To address this issue, this research proposes a novel differential attention metric-based network (DAM-net) that leverages vision transformer (VIT) architecture to capture global interactions and rich contextual information for change detection. SAR images lack obvious visual perception information, such as color and texture, and contain low-intensity areas similar to water bodies, making flood detection more challenging. The proposed DAM-net consists of two key components: a weight-sharing Siamese backbone and a temporal differential fusion (TDF) module. The backbone is split into multiple stages, each comprising three modules: temporal-wise feature extraction (TWFE), cross-temporal change attention (CTCA), and temporal-aware change enhancement (TACE). The TACE module introduces a class token to record high-level semantic information of waterbody changes via the attention mechanism. The DAM-net is evaluated on the S1G Floods open-sourced dataset, a global-scale high-resolution Sentinel-1 Saudi Riyal image pairs dataset covering 46 global flood events between 2015 and 2022. Experimental results show that the proposed DAM-net achieves top performance compared to state-of-the-art methods, with an overall accuracy of 97.8%, F1 score of 96.5%, and IOU of 93.2%. This demonstrates the effectiveness of the DAM-net in accurately detecting flooded areas using high-resolution SAR imagery. Global flood detection from multi-temporal synthetic aperture radar (SAR) images is a challenging task due to complex interactions between the radar signal and the environment. This paper presents a novel approach to address this challenge, introducing DAM-net, a differential attention metric-based network designed to effectively identify and differentiate water bodies in SAR imagery. DAM-net's architecture consists of two key components: a weight-sharing Siamese backbone based on V-TIAV2 for extracting multiscale change features, and a temporal differential fusion module that integrates semantic tokens and change features to generate accurate flood maps. This fusion module explores the relationship between semantic tokens and change features, enabling the network to capture subtle changes in SAR images. To facilitate the development of flood detection methods, this paper also introduces S1G Floods, a new open-source global-scale flood detection dataset. S1G Floods contains diverse flood events and flooded scenes, created using high-resolution Sentinel-1 Saudi Riyal images, and includes various flood causes such as heavy rains, overflowing rivers, broken dams, tropical storms, and hurricanes. Experimental results demonstrate that DAM-net outperforms recent CNN-based and VIT-based methods on the challenging S1G Floods dataset, achieving an overall accuracy of 97.8%, an F1 score of 96.5%, and an intersection over union (IOU) of 93.2%. The proposed approach's excellent performance and good generalization ability make it a promising solution for global flood detection from multi-temporal SAR images. The current state of change detection methods in remote sensing, particularly in detecting floods, is marked by limitations. These limitations are attributed to the inherent locality of convolutional operations and the scarcity of visual information in SAR images. This has led to the introduction of vision transformer-based change detection methods, which have shown promising results but still struggle with flood detection in SAR imagery. To address these challenges, various public datasets for flood detection have been developed. These datasets play a crucial role in developing deep learning-based detection methods, providing essential data for training and testing models. The importance of these datasets cannot be overstated, as they enable researchers to refine their algorithms and improve the accuracy of flood detection. In this context, the paper highlights the need for novel approaches that can effectively utilize the capabilities of vision transformers while overcoming the challenges posed by SAR images. It emphasizes the potential of leveraging these datasets to develop more robust and accurate change detection methods, ultimately enhancing our ability to detect and respond to floods effectively. The limitations of existing flood detection datasets are highlighted, emphasizing the need for a more comprehensive and balanced dataset. The S1G floods dataset addresses these shortcomings by providing a wide range of flood types and locations, including urban, rural, and wetland areas across multiple countries and continents. This dataset's exceptional diversity, generalizability, and balanced class distribution make it a valuable resource for training deep learning models. The DAM-net architecture is then presented, which utilizes a weight-sharing Siamese backbone to extract multi-scale change features from multi-temporal SAR images. It incorporates a class token to record high-level semantic information of waterbody changes and a temporal differential fusion module to predict the flood map. This approach aims to improve the accuracy and dependability of flood detection systems. The proposed deep attention-based multi-temporal network, DAM-net, is a novel approach to identify and map flood events using synthetic aperture radar, SAR, images. It consists of three key modules: temporal-wise feature extraction, cross-temporal change attention, and temporal-aware change enhancement. The architecture is designed to capture both local and long-range dependencies within multi-temporal images. The temporal-wise feature extraction module includes a global dependency branch and a local context branch. The global dependency branch utilizes multi-head attention layers and pyramid reduction modules to model long-range dependencies, while the local context branch employs an image-to-token operation and stacked convolutional layers to embed local context within tokens. The outputs from these two branches are combined and processed through a feed-forward network with residual connections, generating rich temporal-wise representations. The cross-temporal change attention module computes attention weights based on the similarity between the pre-flood and post-flood representations, enhancing the features corresponding to changed regions. The temporal-aware change enhancement module further refines the flood map by leveraging the enhanced features from the cross-temporal change attention module, utilizing a temporal differential fusion strategy to integrate the enhanced features from different stages. This results in an accurate flood map, effectively integrating multi-temporal SAR images to detect and map flood events accurately. The DAM-net architecture is discussed, focusing on intermediate change features obtained by applying stride convolution to reduce the spatial dimension of input images. Representation tokens, denoted as RE, are of size HW, S2I, D, where S equals 4, 8, 16, 32, represents downsample rates and D is the token dimension. The cross-temporal change attention (CTCA) module is introduced, aiming to explore the relationship between multi-temporal images and generate effective change information. This module is based on the attention mechanism, enabling DAM-net to use long-range contextual information to distinguish changes. The CTCA module takes the pre-flood image processing branch as an example, where representation tokens re-pre and re-post serve as query, Q, key, K, and value, V. The cross-temporal attention operation is computed using three different projection matrices, followed by a softmax function and an L2 normalization operation. The output of the CTCA module is then fed into a multilayer perception, MLP, and a residual connection to generate the change feature phi-pre. A similar process is performed for the post-flood image processing branch, yielding phi-post. The temporal-aware change enhancement (TACE) module is proposed to address the issue of losing change information due to different imaging conditions. The TACE module explores the semantic correlation between the representation and change feature of each temporal image, enhancing the change features. The DAM-net architecture is designed to generate enhanced change features from multi-temporal SAR images. It processes the input images separately through pre-flood and post-flood branches, utilizing a multi-head attention module, a PCM module, and an FFN module to produce intermediate outputs. These intermediate outputs are reshaped and concatenated to form enhanced change features, which are then processed at multiple scales. To enhance waterbody change detection accuracy, a class token is added to the pre-flood branch, providing high-level semantic information on waterbody changes. The process involves exploring the relationship between multi-scale change features and the semantic token through a temporal differential fusion module, ultimately generating a flood map. The network is trained using a combination of contrastive loss and dice coefficient loss, with the S1G floods dataset providing a comprehensive platform for training and testing flood detection models. The S1G floods dataset is a comprehensive collection of 5,360 image pairs from Sentinel-1 SAR Imagery, capturing 46 severe flood events across 6 continents. This dataset aims to provide geographic and contextual diversity in flood detection, encompassing various flood scenes and causes. To ensure accuracy, data annotation employs a semi-automated labeling strategy followed by manual refinement. The dataset is structured into training, validation, and testing sets, with an emphasis on representing different flood causes and scenes. For testing purposes, large-sized images are included for flood inundation mapping. The S1G floods dataset is designed to advance the development of effective flood detection methods, particularly by evaluating the practicality of various detection methods. The S1G floods dataset table on page 9 of the research paper presents comprehensive descriptions of global flood events. It spans across continents including Asia, Europe, Oceania, South America, North America, and Africa, encompassing a variety of flood causes such as heavy rain, cyclones, tropical storms, broken dams, and hurricanes. Each event is detailed with information on the continent, location, event date, image size, absolute orbit path, and flood cause. The symbol indicates the presence of multiple images of post-event flooding, while denotes the inclusion of an external test set. This dataset provides valuable insights into the geographical distribution and causes of flood events worldwide. The comparative analysis of DAMnet with other state-of-the-art change detection methods involves a detailed examination of architectures such as FC Siam Conc, DTCDSCN, SNU Net CD, Siam Nested U-Net, BIT, and SWIN SU-Net. Each method's unique features and advantages are highlighted, along with implementation details including the use of PyTorch, NVIDIA Grid RTX 8000 GPU, and specific hyperparameters. The training process employs stochastic gradient descent with momentum for CNN-based methods and AtomW for SWIN SU-Net and DAMnet. Data augmentation through image transformations is also adopted. Performance metrics include precision, recall, F1 score, overall accuracy, and intersection over union, defined using true positive, true negative, false positive, and false negative values. The comparison on the S1G floods dataset in Table 3 shows FC Siam diff performs poorly among CNN-based methods, while DTCDSCN, SNU Net CD, and Siam Nested U-Net improve performance through larger receptive fields, attention mechanisms, and dense connections. SWIN SU-Net and BIT demonstrate competitive precision without complex structures, highlighting the importance of modeling long-range dependency for flood detection. However, they are limited in modeling locality and multiscale feature integration. The proposed DAMnet achieves comparable recall and the highest scores on precision and F1 score, with a significantly lower computational cost than Siam Nested U-Net. Figure 8 provides visualizations for intuitive comparisons. The paper examines the efficacy of DAMnet for flood detection and large-scale flood inundation mapping. It compares DAMnet's performance with state-of-the-art methods on the S1G floods dataset, showcasing a 96% detection accuracy. Visualized in Figure 8, DAMnet successfully differentiates between flood and non-flood areas across various environments. The model's capabilities are further demonstrated through large-scale flood inundation mapping experiments using Sentinel-1 SAR images from Nebraska and Iran. Figures 9 and 10 illustrate the flood inundation maps, highlighting DAMnet's ability to generate detailed and accurate flood maps despite challenges posed by agricultural irrigation, complex land use categories, and seasonal changes. The application of DAMnet for flood inundation mapping in the Nebraska region highlights the effectiveness of the overlapping embedding layer in preserving local continuity, as demonstrated in Figure 11. The study emphasizes the significance of land cover information provided by the S1G floods dataset for post-flood evacuation, protection planning, and disaster assessment. The ablation study on the module effect verifies the importance of the cross-temporal change attention and temporal-aware change enhancement in improving performance. The use of the semantic token is also shown to be beneficial. The flood inundation mapping results of the Iran region using the proposed dam net model demonstrate the effectiveness of the approach. Figure 10 illustrates the flood inundation mapping of the Iran region, which spans 261.638 square kilometers and was affected by flooding on January 13, 2020. The figure comprises a pre-flood optical image, post-flood SAR image, and flood mapping of the yellow box region. To evaluate the performance of dam net, the authors incrementally add modules to the baseline model. Initially, the baseline model achieves modest performance metrics, with an overall accuracy of 1.3%, F1 score of 2.1%, and intersection over union of 1.8%. However, the addition of the change token-based contextual attention module and temporal attention-based contrastive embedding module significantly improves performance, particularly in terms of intersection over union, with a 5.5% increase. This underscores the importance of identifying change features using global contextual information and addressing information loss issues. Furthermore, the introduction of the semantic token component enhances the model's ability to distinguish waterbody changes from other types of changes. As shown in Figure 11, changes caused by temporary objects, such as ships, are effectively suppressed. Consequently, dam net with all modules outperforms the baseline by a large margin, achieving an overall accuracy of 98.8%, F1 score of 95.3%, and intersection over union of 92.6%. The authors conduct an ablation study of the proposed dam net model on the S1G floods dataset, as presented in Table 4. This study assesses the model's performance with and without its key components, including the overlapping embedding layer, OEL, the combination of CTCA and TACE modules, CASE, and the semantic token, ST. The results demonstrate that each component's addition contributes significantly to performance gains, with the full dam net model achieving the best results in terms of overall accuracy, OA, F1 score, and intersection over union, IOU. Figure 11 visualizes the ablation experiment, illustrating the detection results of the baseline model and its variants, including the full dam net model. The figure shows that the dam net model produces more accurate flood maps compared to its counterparts. The proposed dam net model is significant in addressing the flood detection problem using high-resolution Sentinel-1 SAR image pairs. The temporal differential fusion module in dam net is instrumental in exploring the relationship between semantic tokens and change features, leading to more accurate flood maps. Furthermore, the authors introduce the S1G floods dataset, designed to train and evaluate flood detection models for Sentinel-1 SAR image pairs. This dataset contains a diverse range of flood events with varying causes and richer inundation patterns. Flood detection using remote sensing data has garnered significant attention in recent years. However, existing CNN-based approaches have inherent limitations. In contrast, vision transformers have emerged as a superior alternative. This review provides a comprehensive overview of flood detection methods, highlighting the shortcomings of traditional CNN-based approaches and the advantages of vision transformers. To address the lack of diverse and comprehensive datasets, the authors introduce the S1G floods dataset, which encompasses a wide range of scenes, including wetlands, riverine areas, and urban regions. This dataset provides a more realistic and challenging environment for flood detection models. The authors propose a novel method that leverages the strengths of vision transformers and demonstrate its effectiveness across all evaluation metrics. The results show significant improvements over traditional CNN-based approaches, highlighting the potential of vision transformers in flood detection. The S1G floods dataset is a significant contribution to the field, offering a more comprehensive and diverse range of scenes than existing datasets. The proposed method's superior performance underscores the importance of adopting vision transformers in flood detection applications. The authors acknowledge the support of the China Scholarship Council, which enabled this research. This study contributes to the development of more accurate and reliable flood detection methods, which are critical for disaster response and management. This reference list compiles a range of research papers and articles, focusing on remote sensing, image recognition, and flood frequency analysis. The cited works span across these interconnected fields, highlighting the multidisciplinary nature of the research. Remote sensing, as an essential tool in environmental monitoring, is represented by papers discussing satellite imagery for land surface observation and its applications in hydrology. These studies emphasize the importance of remote sensing in understanding and predicting environmental phenomena such as floods. Image recognition, a key component of machine learning and computer vision, is also well represented. Papers cited explore various algorithms and techniques used for image classification, object detection, and segmentation. This body of work underscores the potential of image recognition in interpreting and analyzing satellite imagery, particularly in identifying and assessing the impact of floods. Flood frequency analysis, a critical aspect of hydrology, is covered through papers examining statistical methods for predicting future flood events. These studies delve into the use of historical data, probability distributions, and climate change projections to estimate the likelihood and potential impacts of future floods. The compilation of these references demonstrates the interdisciplinary approach required to tackle complex environmental issues. By integrating insights from remote sensing, image recognition, and flood frequency analysis, researchers can develop more accurate models for predicting and mitigating the effects of floods. This comprehensive reference list serves as a valuable resource for those seeking to understand the diverse methodologies and applications involved in this field.